All right, we're going to talk, shockingly, about resonance again. So this shows up over and over again. So we're in a new chapter today for our Amines chapter. This is our final chapter, everyone. That's pretty crazy, right? We made it to the end of OChem 2, or close to the end. Most of you, this will be your last chemistry class. So well done making it to the final chapter of this journey. So we'll see amines as nucleophiles, and we'll see some of the sort of standard things that we see when we learn about the functional group at the beginning of the chapter. So we only have a single learning objective today, but it's a little bit in depth. So let's go ahead and jump into it. I will also say that Juan here is your impact scholar, and so he's going to be teaching on Friday as well. So that's part of the announcements. Let me write that down so everyone knows that when I upload the slides. So you'll get to learn more about it. Right, let's go ahead and jump into this. All right, so as I said, we only actually have a single learning objective. So chapter 22A, our first one. So we're going to evaluate the structure of amines as it relates to basicity. So amines are our best neutral bases out there. So if you're following along, this is chapter 22.2 in your book. All right, so amines are quite nucleophilic. They're quite basic. When we take a look at why that is, let me draw out sort of the structure of amines. Some of our naming for that, and then we'll talk about some things related to periodic trends. All right, so we have a nitrogen here, and if it has one R group, typically a carbon-based group, and 2 protons, we would call this a primary amine. So this is a primary amine, and meaning R equals that carbon-based group. Right, so we would call this a primary amine, but I'd like to contrast that naming to you to alcohols, all right? Alcohols, we call this a primary alcohol, right? And it meant something different to call it primary, right? So it meant that we just have, a primary alcohol means we have one R group attached to the carbon. All right. And amine means, a primary amine means we have one R group that is attached to the nitrogen. All right. So I just want to get this naming sort of settled for us. All right. So you guessed it, a secondary amine has 2 carbon-based groups, 2 R groups on it. All right. This is our secondary amine. And we'll contrast that to our secondary alcohol, which just had 1 hydrogen bound to the carbon, bound to the oxygen, right? Because if we were to add another carbon to our oxygen as sort of analogously to our amine, that wouldn't be a secondary alcohol anymore. That would be an ether, right? So I just want to make sure everyone's sort of on the same page of this naming, because I wouldn't say it's in contrast to what we know. We just need to recognize what we're talking about when we say this. All right, so tertiary amine is, of course, something that has 3 R groups on it. And we can, of course, contrast that to a tertiary alcohol, which the carbon bound to the oxygen has 3 R groups on it. All right. So I just want you to recognize this. So you don't kind of get tripped up and say, well, why is it that we have sort of a different naming system? Let's just recognize it so we don't get tripped up on it. All right, something that we don't have for alcohol naming is a quaternary amine. So this is an amine. It turns out to be an ammonium. So we're going to take that lone pair of electrons and we're going to replace it with an R group, meaning that this is going to have a positive charge. All right, so this is a quaternary quaternary amine, and we call that and ammonium. So we might not have seen this word before. Quaternary amine. All right, this means it has all carbon-based groups on it, all right? So if we just had something that had a bunch of hydrogens on it, but had our amine protonated, we wouldn't call this quaternary, we would just call this an ammonium salt. All right, so we sort of hold a special place for when we have our carbons bound to our nitrogen. All right, that's just sort of a formalism. Not something to focus on too much, but I just want to be technically accurate with you. Okay, so why are these such great bases? Well, we take a look at the periodic table and we see that nitrogen is electronegative, right? But it's not as electronegative as oxygen and certainly not as electronegative as fluorine, so it's element number 7. We see that it likes to have 3 bonds to it, so we have a lot of carbons and a lot of electron density that can be donated to our amine if we have 3, for example, carbons on it, or even just 1 or 2. So it becomes a very, very good neutral base. All right. Okay, so let's talk a little bit about the structure. All right. Let's talk about this hybridization. So we've seen other nitrogen-based functional groups and taken a look at some of that hybridization, and I'll go ahead and bring that up for you. When we talked about amides, I'll remind you we talked about this. All right. Let's spell this right. All right, so let's talk about the hybridization of that nitrogen. Okay, so if we were to draw this out, we see that we have a lone pair of electrons on our nitrogen in this orbital here. And we can see that we can sort of draw out some characteristics of the structure of this amine. And we see that this is an sp3 hybridized center, all right? So we can sort of draw this as an sp3 hybridized center. Right, if we're counting that lone pair. So we would say 3 substituents, so whether that be hydrogens or R's, plus 1 lone pair equals sort of the sp3 hybridization, all right? If we were not going to consider that lone pair, we can think about sort of a different way to think about this. So let me draw this in a different color. Okay, so if we don't consider the lone pair, then we have a trigonal pyramidal structure. All right, so if we just kind of think about our nitrogen here, our bonds here, right? This is sort of like a tripod of a shape. All right, so that lone pair is really, really important for us because it's going to act as our base. But we also sort of need to think about the steric environment because the lone pair isn't really imparting too much steric environment around it. So it's weird to have to think about 2 sort of forms of a type of functional group, but it's quite important as we think about basicity as it relates to things like sterics, all right? All right, so let's contrast this to what we saw before. We have very decidedly a sp3 hybridized carbon for an alkyl amine, all right? To when we saw the situation with amides. Right, so we've seen nitrogen as a functional group before. We can have an amide that looks like this, right? And we drew resonance structures of amides where we took our lone pair of electrons in our nitrogen and we made a carbon-nitrogen double bond and broke our carbon-oxygen double bond. Right, and that resonance structure has our oxygen with a negative charge which is kind of okay with, right? It's a very electronegative atom. And our oxygen negatively charged and our nitrogen positively charged, all right? So in this case, we said our nitrogen in our amide is between sp3 and sp2 hybridized. All right, because we have this other resonance structure that would make this into an sp2 hybridized nitrogen. All right, this would not be a tripod here, even though we sort of see three separate things bound. This would be in the plane of the board, all right? So it'd be a trigonal planar, not a trigonal pyramidal structure, right? Meaning that the availability of the lone pair in this resonance structure doesn't exist, all right? So I think it's really important when we sort of understand the reactivity of one functional group to kind of put it in the context of a new functional group for us, all right? It turns out we've actually seen amines throughout this book, but this is kind of the culmination of everything that we've seen thus far. Okay, so this is going to be, and I will specifically say here that this definition up here best applies when R equals alkyl. All right. All right, so we get that nice, always sort of, we can think about that without any exception as sp3 hybridized. Okay, and we contrasted that to our amides. Now let's take a look at what aromatic amines can look like, all right? So say our R is a phenyl group, for example. So R equals an aryl group, some substituted aryl group, okay? These compounds are called anilines. Those are the common name for it. Okay, so we have our nice sp3 hybridized. We sort of contrasted that to our amide. Let's take a look at our aromatic amine. All right, so we have an aromatic amine. We'll just start with aniline itself. We'll have some hydrogens. We have our lone pair of electrons here. All right. So unlike the resonance structure here, where we could delocalize our negative charge on a really nice electronegative element, we don't really have the option to delocalize on a really electronegative atom, but we still have some valid resonance structures for this structure here, all right? So let's go ahead and take this lone pair of electrons on nitrogen, and let's make a CN double bond, and then that breaks the CC double bond. We can place an anion on that carbon. All right, so that is breaking aromaticity, so not particularly favored, but it is a valid resonance structure, all right? So now that lone pair of electrons and that negative charge is on the carbon, okay? We can do this again. We can stabilize that negative charge by moving it around our ring. Now we can make a CC double bond at that next carbon and break a CC bond and place it at that carbon para to our nitrogen with this series of arrows. Okay, so we can undergo yet another way to stabilize that negative charge and those lone pairs of electrons. That is technically, oh, you know what? I forgot a positive charge on our nitrogen. Sorry about that, in our first structure or middle structure. So be sure to add that in. Right, so resonance is, even though we don't have a nice electronegative atom to stabilize that negative charge like we do in the amide, because we have so many valid resonance structures, we can go ahead and draw one more. That starts to become a pretty stabilized negative charge. So we can use that negative charge, that pair of electrons, to make a CC bond and break that CC double bond, right, and getting us to our final resonance structure. I'll go ahead and move some things over so we can fit it on the page. All right, so that final valid resonance structure we see has that lone pair that's been delocalized throughout that negative charge on that carbon. Right? So that means when we have an aniline and structure with an arylamine, these turn out to be similar. Anilines are a bit more similar to amides than they are to amines. All right, so these are between sp3 and sp2 hybridized because of resonance. All right, so it's kind of, that's why we only have one learning objective today. It's kind of involves, all right? So the TLDR is we can't just say the hybridization of an amine is sp3 hybridized. We need to understand what else is on our amine structure, okay? So why do we care, right? You should always ask yourself that question. Why am I being taught this? Well, I told you that amines and nitrogen is sort of an excellent base for deprotonation. It's a neutral base. It's very mild, but strong at the same time. So we need to think about using this as a base. So what is going to be a better base? What is going to be more hydrophilic? So I'm going to test before telling you the answer. I'm going to sort of see how you all think about this, considering the fact, so this will be our chime-in question, considering the fact that we have to think about the hybridization, what happens when we hybridize that nitrogen, it's an sp3 versus when it's an in-between sp3 and sp2, all right? So I know I haven't told you the answer to this yet, so this is going to be a bit of a stretch question, but I kind of want to see where we are in terms of thinking about how hybridization could affect basicity, right? When we're a base, we need that lone pair to deprotonate. I'll give you that hint. All right, you're welcome to chat about it with your neighbor if you like. We'll wait for everyone to kind of weigh in on this. All right, we have quite a few people weighing in, so let me go ahead and see where people are at here. All right. Yeah, we're kind of tied here, right? Before I displayed it with the right answer. So we were kind of 50-50 about what is more or less basic, all right? So I'll let people answer, the few people haven't answered, go ahead and have a chance to answer, and then let's talk about why this is. It turns out the aniline is less basic. That lone pair of electrons is tied up in resonance, so it can't act as a base, right? Okay, so looks like everyone's finished answering in. I'll go ahead and close this. All right, so the implications of what we just talked about are found in our chime-in question. Okay, so we were contrasting aniline versus the alkyl version, the fully saturated version of this molecule. All right, I'll draw on our lone pair suggestively. So this aniline is less basic. Our cyclohexylamine is more basic. All right. And that's because this lone pair here is tied up in resonance. So less available deprotonate. Versus our cyclohexylamine, this is not tied up in resonance. So it can just be hanging out there for us to use as a base. Okay. So let's go ahead and get into a couple of pKa's and see kind of where we're at when we have these relatively strong bases. Okay, so as I said, amines are the strongest neutral base that we have learned. All right, and are gonna learn because we stop at the amines chapter. All right. So a higher basicity is equal to a weaker conjugate acid. All right, so these are our pKa rules. All right, so a higher pKa. Okay, so let's take a look at what this looks like. So here we have some alkyl amines. Let's start there. All right. We have our amine here. That's our base. Let's have acetic acid, all right, as our acid. So we've seen acetic acid before. So acetic acid. This has a pKa of 4.7. And so if we put these two things in together, I said that your amine base is a great neutral base, all right? So we're going to have an equilibrium here. And our equilibrium is going to have a KEQ of 10 to the 6th. So it's really going to lie on the product side here, which is going to be our ammonium that's been protonated. And our counterion is our acetate. All right. And so we can't say an amine has a pKa. Well, we could say an amine has a pKa, but we're really talking about the pKa of the conjugate acid. The pKa of 1.6. So that means that our amine is a better base than our conjugate base of acetate. All right. So when we're comparing the pKa's, this wins out, which is why the equilibrium lies so far to the left. All right. So that's kind of a nice baseline, 10.6. Now we talked a lot in this class about different trends, right? You talked about trends with electron withdrawing groups, electron donating groups. Amines are a little bit of an outlier. So I'm going to put trends in parentheses, all right? Or sorry, not parentheses, quotation marks. So trends with alkyl substitution. All right, so let's start with an amine here. So our amines are H2NMe. That's the one we just learned. And we said the pK of the conjugate acid was 10.6. All right, so you might think, well, adding a little bit of an electron, more electron density could make this into a stronger base. So adding an ethyl group, more carbons, a little bit of electron density. Might be onto something there. A little bit of a stronger base. Okay, not really. We really haven't changed much when we added more electron density. What about if we added another methyl group? Instead of an ethyl group, 2 carbons, we added another methyl group to the amine itself. Maybe we would be able to make that into a better base. Not so much, right? 10.7. These are all kind of the same. All right, well, let's add another methyl group and let's see what happens. So if we have another methyl group, we have trimethylamine. We're at 9.7. Okay, so no real trend here. Okay, all of them are around 10 to 11. So that's the information that you need to know. If you're wondering why that is, it's not a part of the learning objective, but it has to do with the availability of that lone pair. So as soon as we start to add more substituents around our amine and different sizes of substituents, we change the steric environment. We actually change how sort of trigonal pyramidal we are, and the availability of that lone pair as that p orbital that the lone pair is in kind of gets a little bit rehybridized. So if you're curious, that's the reason why, but I'm not going to write that down because you don't need to know that information. Just for those of you who are curious, that's why. It has to do with that sort of small amounts of sterics affecting slightly the rehybridization around that steric environment. So good news is that we do have some trends for aromatic amines. So before I put this in quotation marks, so we do have different trends for aromatic amines. Right, we call these anilines. All right, and this should make sense. Why should this make sense? Let's go ahead and take a quick look back at what we saw before, okay? We saw different resonance structures for that lone pair on our nitrogen to engage in and resonate around this ring, okay? That changed the basicity of our lone pair on the nitrogen, right? It made it less basic. Well, you can imagine if you didn't just have one phenyl group that you could resonate into, but say you had another one over here. Say you had another one over here, right? That's going to allow more resonance structures, which is going to change the basicity. So that is why we have trends for our aromatic amines, all right? So again, we'll make a chart here. We have our amine here. Let's have our pKa of the conjugate acid. All right, so let's start with aniline as our first amine, just one substituent, one phenyl group on our nitrogen. And the pK of the conjugate acid, so once this is protonated, is 4.6. Right, so what happens, right, when we added another methyl group above, we really didn't see anything really affected. So what happens based on resonance, we should assume and kind of deduce that this will be affected because this pKa goes all the way down to 0.8, the pKa of the conjugate acid. Right, so this diphenylamine is a pretty bad base. Right, the lone pair is now tied up in resonance with 2 of those phenyl rings. All right, so let's keep going. Let's add on another phenyl ring that we can resonate into. And of course, you guessed it, this is going to have be an even weaker base, and the pK of the conjugate acid is -5. All right, so that's a huge amount of difference. That lone pair is really unavailable to serve as a base, okay? So yeah, so the trend here is more aryl groups equals worse base. And this is because there are so many stabilizing resonance structures. You know, no matter how unfavorable it is to break aromaticity, you can still do it because you can resonate around that entire ring, all right? So this is just a really, really, really bad base. Okay, so, you know, when we added more electron density around our aryl amines or our alkyl amines, we don't really see very many trends, but we know aryl groups can have a lot of substituents. So let's take a look at what happens when you have some substituents on here, all right? So what if we have an aniline with, for example, a methyl group on it. Right, so what have we done here? So before we had a pKa of the conjugate acid is 4.6. This pKa is going to be 5.3. Right? So what we've done here is, of course, we've added electron density to the ring. Right? So that makes it a better base. Yeah. The reason is that if we have a more electron-rich ring, in that resonance structure that I'll refer to yet again, right, we're trying to stabilize a negative charge. And if you have more electron density, that's a less stabilized negative charge. It's less likely to engage in this resonance structure if you have electron density sort of destabilizing that negative charge, right? So it's all about those resonance structures. All right, so what do you think if we put something like a nitro group on our aniline ring? Okay, I'm going to draw that nitro group out for you very suggestively. All right, so what do we think about the resonance structure here? All right, let's draw a resonance arrow. If we're going to resonate, that lone pair of electrons on the nitrogen can come and form a carbon-nitrogen double bond. That can go ahead and have our ring undergo resonance. We can resonate all the way into that nitro group. Okay, and so when we draw that out, this is good review for the final. And thinking about all your EAS reactions and SNAR or NAS reactions. All right, so here's what our resonance structure is giving us here, right? But now, where is our negative charge here? Our negative charge is not on a carbon. Our negative charges reside on these really electronegative elements of oxygen, right? That's very favorable for them to do, right? So here in this case, our nitro group withdraws electron density and stabilizes the resonance structure. All right, so this is a way worse base. All right, so electron density added to the ring makes it a better base. That makes sense, more availability of the lone pair. You don't need to know absolute pKa's. We just need to understand what happens when we have this type of electron density. All right, any questions about that? Right, so it's kind of a hard concept when we're thinking about alkyls and aryls and how those affect things. Those are kind of some of the first time we really considered how much the substituents really affect our reactions. Okay, so we still have about 13 minutes of class, but I always give at one class period about 10 minutes for you all to fill out your teaching evaluations. You're all very busy people, so I don't want you to have to take out time out of your day. So I'm going to leave the room and your TAs will leave the room because we're not allowed to be here when you fill them out. But if you would do that, I would greatly appreciate it, right?